Hi, I'm Mike Bruns from Cascade Stream. Today is August 5, 2018, and we are demonstrating this little computer. This is a AMS905XCC computer made by Libra Computer Company, also nicknamed Le Potato. Le Potato is a single board computer modeled in the form of a Raspberry Pi. It has a different processor than Raspberry Pi. This one has an Amlogic S905X processor with a quad-core ARM processor and a Mali GPU with a video processing unit capable of decoding HEVC at 60 frames per second. As you can see, there are very few components on the board. Really only just the S905X processor chip and some memory chips, all of which are hidden underneath the heatsink. It also has 4 USB connectors, Ethernet 100 base T, a single HDMI output. Power connector is a micro USB. This debug cable provides a serial UART console connection to another computer. It's not required to run this, but when bringing up the board, it's very handy to have it to get the console debug messages from boot time. You can see that I have a heatsink and a fan attached to the processor and memory chips. When I was testing, I was monitoring the temperature of the processor, and it never really went above 50 degrees Celsius, which is not very hot for a processor. However, I was experiencing spurious kernel panics and other freezing behavior in certain circumstances. These went away after I attached the heatsink and the fan. The representative from Libra Computer expressed that there is no heat spreader inside of the chip package, and so the external heatsink is very helpful to function as a heat spreader to avoid hotspots on anywhere on the chip die. There are a number of manufacturers making single board computers like this. We chose the one from Libra Computer because we understood they're working with a company called Bay Libra to port the Amlogic specific device driver components to the mainline Linux kernel. This opens up the possibility of having a software operating system and development environment that is on the mainline kernel. This is a very attractive prospect for having highly supportable software moving forward. Turning on the computer, we are demonstrating Kodi software. This is a full-featured home entertainment software system that's open source software. The system boots up in about 30 seconds and puts the user into a graphical user interface environment that is similar to Apple TV or other Roku or other home entertainment software systems. From here, we can select videos to play from files which are stored on the microSD file system of this card. For example, here's the Meridian movie, which is 10-bit HEVC. The delay you see on startup was the television switching from the 1080p resolution that implements the graphical user interface to the 4K P60 resolution that the movie is currently playing. This info screen shows the resolution in the upper left-hand corner. Studying the playback carefully, we see that the image is pristine and it is delivered correctly to the output video interface. There's no tearing. It is being delivered at 60 frames per second, and it is reaching the set in its full pristine format. This board also has VP9 decoding capability. Switching back to 1080p for the user interface. Now starting up a VP9 clip. The resolution of this material
start. 4, 3, 2, 1.
is 4K by 2160.
Jerk, Tom. Look, Celia, we have to follow our passions. You have your robotics, and I just want to be awesome in space.
Why don't you just admit that you're freaked out by my robot hand?
I'm not freaked out by it. All right, fine. I'm freaked out. I'm having nightmares that I'm being chased by this giant robotic clown.
Whatever, Tom. We're done.
I think that guy just lost a girlfriend. We're running a Kodi image, Kodi software that's part of the CoreLEC image. This was built on my computer from all software sources. The instructions for building the CoreLEC image are actually on the LibreELEC website. And it explains how to download all the sources, which takes between 1 and 2 hours. I then built this on a dual quad-core Xeon system. Building this image from software sources took between 2 and 3 hours on that system. What the image consists of is a stripped-down version of the Linux operating system with just those system services and libraries needed to support the Kodi application. It results in an all-in-one software image that you can install on the micro SD card. Once installed there, you can boot the single board computer directly. This approach is a good way for deploying software, but it doesn't include a package management system or other tools needed for software development. So really this is a nice way to deploy software, but not to develop software. Again, the main goal of demonstrating the Kodi application is to show the hardware capabilities of the device. We're seeing the 4K resolution at full frame rate, and we're seeing it work correctly. The way this is implemented in this image, using the Kodi application on the CoreLEC build, is using proprietary drivers that are provided by the M-Logic chip manufacturer. These libraries and device drivers are specifically designed to work with the Linux kernel version 3.14, which is quite old. They cannot upgrade to a newer version of the kernel without having to update the libraries to match. And there is no ongoing effort to do this. This is a proprietary driver approach for deploying the system capabilities of this processor. And what we're going to see in a moment is a step on the path towards supporting these hardware capabilities using the mainline Linux kernel and the very latest operating system software. Next, we'll shut down the computer, change the memory card, and install one that has the Ubuntu operating system image on it. Removing the micro SD card that has the Corelec image on it with the Kodi software. And installing another micro SD card onto which we've put the Ubuntu image. This is what the single board computer looks like now, with all devices connected to it: mouse, keyboard, network, HDMI, power, and this last wire is the debug serial UART connection to the computer. We're going to watch the console display as we turn on the computer that has the Ubuntu image in it. These are the initial bring-up messages from the operating system. The graphical user interface doesn't turn on until the boot process is nearly completed. So if anything goes wrong during the boot process, this UART connection is essential to understand what went wrong. Once at the login prompt, we can actually log into the computer. A full console is provided. One of 3 different consoles that you can get to on the Ubuntu operating system. We are running Ubuntu 18.04 long-term support version. This is based on the Linux 4.14 long-term support mainline kernel. This is the login prompt, and it is being presented at a 1920 by 1080 resolution, even though the TV set is a 4K set. We spent a day trying to figure out how to get this computer to recognize and provide the user interface in a 4K resolution. We still haven't figured it out. The problem may have nothing to do with the single board computer or the Ubuntu software image that we're running. This may be an issue with the TV set advertising to the computer that it is a 4K compatible television. I see no evidence that the computer has received the 4K resolution information in the EDID information that was transmitted between the TV and the operating system on startup. Before we log in through the normal user interface, let me jump over and show the console interface. I'm pressing Control-Alt-F2. That stops the user interface and switches to a simple TTY type interface you can see in the upper left hand corner. Logging in. Username is Libra. Password is computer. And this is providing another console interface. This is the second way of logging in to a console interface to the Analogic computer. One of the things that I can show is what are the resolutions that the television set has advertised to this system can be used. These are contained in this file. You can see the list ranges from 1920 by 1080 at the top, all the way down to 640 by 480 at the bottom. And absent are the 3840 by 2160 or the 4096 by 2160, modes that the television is capable of. Now we'll press Ctrl-Alt-F1, going back to the normal user login. Entering the password, which is the word computer. This is starting up the user interface for the Ubuntu operating system. This single board computer with a file system based on a 16 gigabyte micro SD card and 2 gigabytes of RAM is providing a full Ubuntu desktop computer experience. The response is a bit slow, I think, because of the read and write characteristics of the micro SD file system. But otherwise, it's giving all of the facilities and experiences you expect from Ubuntu. For example, I can open the settings. Go to the display device. Try to change the resolution to 4K, but this is not an option. We'll keep trying to figure out how to get that to work. Now I'm going to show a C++ workflow for building and running the FFmpeg application. I'll open a console window. Install the G++ compiler. This is using the APT interface to the Debian package management system that's part of Ubuntu. It's a great system. It automatically downloads other libraries that are dependencies of the G++ compiler and installs them all together. Again, this is all running on the Load Potato single board computer. Next, we will download the FFmpeg software, source code, changing directories to the FFmpeg source files. FFmpeg uses a software build system based on configure and make that is very familiar in the Linux world. We'll run configure with some options. This takes a while. What's running now is the configure step for FFmpeg software build. You can see that this is a moderately intense, CPU intense process. The memory usage shows 1.2 gigabytes of RAM are in use. Some of the swap partition, which is only 700 megabytes in size, has also been used. The configure step is completed. We can scroll back to see what it found. Enabled output devices, FBDev, which is a direct interface to the frame buffer part of the operating system provided by the Linux kernel. It is listing a video for Linux output device through the V4L2 driver. Here's one that I'm looking for. H.263 through the video for Linux memory-to-memory device driver. H.264 through the video for Linux memory-to-memory device driver. Let's see if they have HEVC. Not listed. These codecs are meant to use the hardware decoding capability of the processor. They don't work. But there is enough capability there that the FFmpeg build detected the capability and included them so far in this FFmpeg build configuration. Now that the build configuration is ready, we just type make to start building it. This takes a little while. The FFmpeg build is completed. Now we can type make install to copy the binary files and libraries to the install location. Now FFmpeg is ready to run. There's FFmpeg. Here's FFmpeg starting to decode a binary file. Working just fine. What I want to do now is play this file to the display. We're going to switch now to the console interface that we saw before. This is because we're going to play to the frame buffer output. The frame buffer output is masked by this desktop environment. So we need to go to the console, which doesn't have the desktop environment. Specifying the frame buffer device output. Routing the output to device frame buffer. Let's see if this works. It's playing back as fast as it can. This is 3 to 4 times real time for a 720p clip. We can use a different option on the FFmpeg command line to slow this down to real time. Let me just stop this and we'll add that option. Way back in the beginning, that means played in real time. So I wanted to start to demonstrate building an application from source code and then using it to play a video file directly to the display. But there are some issues. If you look closely, some of the output frames are torn. That means that the video data is being written to the frame buffer in an unsynchronized way compared to the output frame synchronization. I think this is one of the biggest challenges for an application that's decoding and outputting video in this way, is how can it decode to a frame buffer and have the frame buffer be presented to the output HDMI interface in a clean way at HEVC at 4K resolution at 60 frames per second without any skipped or repeated frames or without tearing. This involves an understanding of how these facilities are handled in the Linux kernel and in the Ubuntu operating system. It probably involves the video for Linux device driver. However, when I run FFmpeg in this way, specifying the video for Linux device output, I do get an error message and it does not work. It probably just is an indication that the device driver for the hardware output capability for video for Linux for this processor is not yet finished in the mainline kernel. But this is work in progress. I don't have a good indication of when this work will be completed. It's quite possible that completion for a basic level of operation is less than 1 year away. I think it's unlikely that we will see this working in a nearer term, in 1 or 2 months. I don't think they're working on it that fast. There are a lot of things on the list that the mainline kernel developers are working on that have higher priority. But everyone is interested in demonstrating the output video pipeline and the hardware decoding capability working from the mainline kernel device driver on this processor using the Linux kernel. I wanted to see if we could composite the output from 2 decoding instances onto the frame buffer to display at the same time. So I wrote a script to start FFmpeg twice. Now running that script does show 2 simultaneous playbacks. I intentionally added a 2-second delay between them. This works because it's doing software decoding. It's not using hardware decoding on the Amlogic device because the device driver isn't ready yet in the mainline Linux kernel. This is as close as I could come to showing multiple playback at the same time with this version of the operating system and kernel. And again, even after spending a day trying to make it work, I was not able to get the frame buffer to appear as a 3840 by 2160 resolution output. One last thing I'd like to show is a debugging workflow. For this, I'm going to log into the single board computer through the SSH login. Password is computer. This is the 3rd way to get a console interface onto the Ubuntu operating system. I'm going to run GDB. The command line is gdb-args local bin ffmpeg, followed by all the command line arguments that we used in the previous video playback demonstration. GDB starts. If I type run, it will start running the application. It takes a little longer to start up because it's loading symbols. And it's playing on the monitor, as we saw before. The difference is now it's playing in the debugger. So let's stop the process. Let's set a breakpoint. libav device. And let's on line 116. And now when I continue, it will stop on the breakpoint. I can use GDB commands, next line, examine variable values, if I can remember how to do that in the command line interface. List is providing a source code listing of where we are stopped. I think I can type print and then a variable value name, PIX format, is given the variable value name. So this is GDB. Why am I not running GDB in a GUI? The way I usually like to do this work is using the Eclipse GUI with the C development tools. That's a great development environment. It has indexing and excellent symbol search capabilities. However, the amount of memory that's provided on this computer prevents me from running a full-featured GUI like Eclipse. But the basic development tools, compiling and debugging, do work. So for a small application, it would be no problem to do native software development on this computer. For a very large application like FFmpeg, it might be better to use a cross-compiling approach where you're using a large workstation type of computer with lots of RAM that you can run Eclipse on. Compile it using a cross-compiler, and then maybe have a remote debugging setup where the GDB interface is running on the host, but it's debugging a target on the single board computer. From what I've seen so far, all of these development approaches are viable with this computer, and they're working now. By the way, the cross-compiling approach is exactly the approach that's used for building the Kodi application software in the Core Elec image that we talked about earlier. This has been a demonstration of the AM-S905X single board computer by Libra Computer. We've seen this device playing back HEVC at 4K resolution at 60 frames per second, also VP9, and it did so perfectly, but using a very old Linux kernel and proprietary drivers that are not very maintainable. We have also seen this running the latest Ubuntu operating system with a mainline kernel implementation, and enough of the device features implemented in the mainline kernel to support the basic computer operation and build tools, but not the special features for video playback, such as the video output pipeline through HDMI, not yet fully supported in the mainline kernel at 60 frames per second, and the hardware decoding capability, also not yet fully supported. Okay, that's all we got. We hope you have enjoyed this video demo. For more information, please see our wiki pages on the Bitbucket website. There you will find useful links and detailed instructions to reproduce all of the results you saw in this demo. Until next time, this is Mike Bruns from Cascade Stream, signing off.